Hello and welcome. In this video, we're going to dive into the incredibly fascinating world of organic chemistry. Think of this as your friendly, conversational guide to the subject. Our main goal here is to establish a solid, foundational understanding of the core concepts that define this field. We'll be covering topics like the introduction to organic chemistry, molecular structure and bonding, and alkanes and cycloalkanes. By the end of this session, you'll be able to answer some fundamental questions about what makes organic compounds unique, how atoms are connected within them, and how to describe and visualize their shapes. Specifically, you will learn to define and identify organic compounds. You'll be able to describe how atoms bond using hybrid orbitals, and you'll be able to draw and name simple organic molecules like alkanes. We'll break down each concept step by step with worked examples and some practice questions to make sure everything sticks. So grab a coffee and let's get started. So what exactly is organic chemistry? You might associate the word organic with food or health, but in chemistry it has a very specific meaning. Organic chemistry is, quite simply, the study of carbon-containing compounds. Yes, that's it. It's an entire branch of chemistry dedicated almost exclusively to the element carbon. Now you might be wondering, why does carbon get its own special discipline? What's so unique about it? The answer lies in carbon's incredible versatility. Take a look at its position in the periodic table. You'll see it has an atomic number of 6, which means it has 6 electrons. Specifically, it has 4 valence electrons in its outermost shell. This means it has 4 opportunities to form bonds with other atoms. To achieve a stable octet, it needs to form 4 bonds. The most common type of bond it forms is a covalent bond, where it shares its electrons with other atoms. So, carbon is tetravalent, meaning it forms 4 bonds. But here's the amazing part. Carbon can bond very strongly to other carbon atoms, and it can do so repeatedly. This ability, called catenation, allows carbon atoms to link together to form incredibly long chains, intricate rings, and complex 3D structures. It's like building with Legos, but on an atomic scale. This property is the foundation of all life on Earth. Proteins, carbohydrates, DNA, they are all massive organic molecules built around a carbon framework. In a way, organic chemistry is the chemistry of life itself. Okay, so carbon is amazing. It forms 4 bonds and can link to other carbons. But how do we actually represent these molecules? Scientists have come up with several ways to draw and visualize organic compounds, each offering a different perspective. First, we have the Lewis structure. You might remember this from general chemistry. It shows every atom and every valence electron represented by dots or lines for bonds. It's very detailed but can get messy for large molecules. Let's take a simple example. Methane. Its Lewis structure shows the central carbon atom and its 4 covalent bonds with 4 hydrogen atoms, with the shared electrons represented by lines. It's accurate but clunky. This brings us to the condensed formula. This is a shorthand that skips drawing the bonds and simply lists the atoms in groups. For methane, it's just CH4. For a chain of carbons like butane, it's CH3CH2CH2CH3. It's quick to write but doesn't tell us about the molecule's shape, and it can be ambiguous for complex molecules with branching. For our course, the most important representation will be the skeletal structure, also known as the line angle formula. This is a highly simplified notation that is incredibly efficient. In a skeletal structure, carbon atoms are at the vertices, or corners, and at the end of every line. We just assume they are there. Also, we assume each carbon is bonded to enough hydrogens to satisfy its valency of 4. Bonds to heteroatoms, like oxygen, are shown. This structure instantly shows us the backbone of the molecule. Skeletal structures are the language of organic chemists. They allow us to quickly draw and interpret even very large, complicated molecules with ease. Okay, let's put that into practice. It's time to translate between these different drawing styles. This is a fundamental skill in organic chemistry. Our goal here is to be able to convert a condensed formula into a skeletal structure and vice versa. Think of it as learning to speak 2 different dialects of the same language. Let's work through an example. Suppose we have the condensed formula CH3CH2CHOHCH3. The first step is to identify the main carbon chain. The parentheses here are a hint. They tell us that the OH group is a branch off of the previous carbon. So we have a 4-carbon chain with a hydroxyl group or an OH group attached to the 3rd carbon from the left. Now, let's draw it using the zigzag pattern of a skeletal structure. Each corner and end represents a carbon. Finally, we add the branch. We count the carbons in our zigzag, 1, 2, 3, and attach the hydroxyl group to the 3rd corner. And that's it. This simple drawing contains all the information about the atoms and their connections. We don't need to draw the hydrogens on the carbons because they are implied. Now let's try going the other way. Let's write the condensed formula for this molecule. Step 1. Identify every carbon atom. Here we have a total of 5 carbons, 1 at the top, 1 at the bottom, and 3 in a central chain. Step 2. Starting from the left, write down each carbon and the hydrogens needed to complete its valency. The end carbons, C1 and C5, need 3 hydrogens each. The branched carbon, C3, needs only 1 hydrogen. The unbranched carbons, C2 and C4, need 2 hydrogens each. The branched carbon, C5, is a methyl group, so we can write it as CH3CH2CH, CH3CH2CH3. The CH3 in the parentheses indicates the branch on the carbon that immediately precedes it. Practice this and it will become second nature. We've established that carbon forms 4 bonds. But how exactly does it do that? We need to remember a concept from general chemistry called hybridization. Our objective in this section is to understand how carbon forms stable covalent bonds through the mixing of its atomic orbitals. It's like atoms are making new, better tools for bonding. Let's start with a carbon that forms only single bonds, like in methane. Its electron configuration is 1s2, 2s2, 2p2. If it were to bond using its atomic orbitals directly, it would have 2 lone pairs in the 2s orbital and 2 half-filled 2p orbitals available for bonding. This would result in 2 bonds at right angles and a tetrahedral shape. But this isn't what we observe in nature. The observed shape of methane is a perfect tetrahedron with 4 identical bonds, all 109.5 degrees apart. How can this be? The answer is sp3 hybridization. The 2s orbital and all 3 2p orbitals combine to form 4 identical hybrid orbitals. These new sp3 orbitals arrange themselves as far apart as possible in a 3D space, which creates the tetrahedral geometry. Each of these orbitals can then form a sigma, or single covalent bond. This model perfectly explains the structure of alkanes. Now what if carbon forms a double bond, like in ethylene? This introduces sp2 hybridization. Here, only 1 2s and 2 of the 2p orbitals combine to form 3 sp2 hybrid orbitals. These 3 orbitals lie in a plane, forming a trigonal planar geometry with bond angles of 120 degrees. The remaining 2p orbital is left unhybridized and is perpendicular to that plane. This unhybridized p orbital is what forms the second part of the double bond, the pi bond. This explains the rigid, flat structure of alkenes. Finally, for triple bonds, as in acetylene, we have sp hybridization. 1 2s and 1 2p orbital combine to form 2 sp hybrid orbitals, which are oriented linearly with a 180-degree bond angle. The 2 remaining unhybridized 2p orbitals form 2 separate pi bonds. Together with the 1 sigma bond from the sp orbitals, this makes up the triple bond and the linear geometry of alkynes. So, to recap, the type of bond carbon forms dictates its hybridization. sp3 means 4 single bonds and tetrahedral. sp2 means 1 double bond and trigonal planar. And sp means 1 triple bond and linear. This is a crucial framework for understanding organic molecules. Now that we know how carbon bonds and how to draw its structures, let's look at the first and simplest family of organic compounds, the alkanes. In this scene, you will learn to define what an alkane is, how to systematically name branched alkanes using a set of rules, and to recognize their key properties. Alkanes are defined as saturated hydrocarbons. Hydrocarbon means they are made up of only carbon and hydrogen atoms. Saturated means they contain only single covalent bonds, specifically sp3 hybridized carbons. Their general formula is CnH2n plus 2. For every carbon atom, there are twice as many hydrogens, plus 2 for the ends of the chain. For example, ethane has 2 carbons, so it has 2 to 2 plus 2 equals 6 hydrogens. Its formula is C2H6. Alkanes are nonpolar molecules, meaning they don't dissolve in water and have low melting and boiling points. This is because the only intermolecular forces between them are the weak London dispersion forces. Chemically, alkanes are known for being quite unreactive. Because they only have strong sigma bonds, they don't easily undergo many reactions. The two main ones you'll see are free radical halogenation, which is a substitution reaction, and combustion, which is what happens when you burn them. Now for naming. We use a systematic method called IUPAC nomenclature. Here's how it works. First, find the longest continuous chain of carbon atoms. This chain gives the molecule its parent name, based on the number of carbons. Then you identify any branches, which we call substituents, attached to that chain. You number the parent chain starting from the end that gives your substituents the lowest possible numbers. Finally, you assemble the name, starting with the substituent's location, then the substituent's name, and finally the parent chain's name. Let's do an example. Let's put the IUPAC rules into action with a couple of worked examples. Practice is the key to mastering this. First, let's name this skeletal structure. Remember, every end and corner is a carbon, and hydrogens are assumed. Step 1. Find the longest continuous carbon chain. We can count a chain of 5 carbons in a row. A 5-carbon chain is named pentane. Step 2. Number the chain. We have a substituent coming off the parent chain. If we number from the left, the substituent is on carbon 3. If we number from the right, it's also on carbon 3. So, in this symmetrical case, the numbering doesn't matter. Let's start from the left. Step 3. Identify the substituent. We have a 1-carbon group, a CH3. A 1-carbon substituent is called a methyl group. Step 4. Assemble the name. We combine the location, the substituent name, and the parent chain name. The name is 3-methylpentane. It tells us we have a pentane chain with a methyl group attached at the 3rd carbon. Let's try a more complex one with multiple substituents. Remember the rule to get the lowest numbers. Here's our molecule. Step 1. Longest chain. This one is tricky. If we just go straight across, it's 6 carbons, a hexane. But what if we go down from the branch? C, that's also 6. In this case, either will work, but the straight chain choice is often simplest. So, our parent chain is hexane. Step 2. Numbering. Let's try numbering from left to right. Our first branch appears at carbon 2, and the second is at carbon 4. That gives us 2 and 4. Now let's try numbering from right to left. The first branch appears at carbon 3, and the second is at carbon 5. That gives us 3 and 5. The rule is to choose the numbering that gives the lowest set of numbers. Since 2d4 is a lower set than 3d5, we use the numbering from left to right. Step 3. Substituents. We have 2 1-carbon methyl groups. We use the prefix di to show there are 2 of them, so it's dimethyl. Step 4. Assemble the name. We place the locations and prefix before the substituent name, separated by commas, and combine it with the parent chain. The name is 2,4-dimethylhexane. This precise name tells anyone how to draw the molecule. Remember, the goal is to give the lowest possible set of numbers, and to use prefixes like di, tri, and tetra when you have identical substituents. With practice, you'll be naming complex alkanes in no time. So far, we've talked about straight or branched chains of carbon. But carbon's catenation ability also allows it to form rings. These are called cycloalkanes. Our goal now is to apply the naming and drawing principles we just learned to these cyclic structures. Cycloalkanes are saturated cyclic hydrocarbons. Because the ends of the chain are connected, they have 2 fewer hydrogens than an open-chain alkane. Their general formula is C sub NH sub 2N. Naming is very similar to alkanes. You take the name of the corresponding open-chain alkane with the same number of carbons in the ring, and you just add the prefix cyclo. So, a 3-carbon ring is a cyclopropane, a 4-carbon ring is a cyclobutane, and a 6-carbon ring is a cyclohexane. For drawing, we represent the ring as a simple geometric shape. A cyclopropane is a triangle, a cyclobutane is a square, a cyclopentane is a pentagon, and a cyclohexane is a hexagon. These shapes are a shorthand for the carbon backbone. Now, let's look at naming substituted cycloalkanes. It's essentially the same logic as branched alkanes. Let's name this molecule. It has a 5-carbon ring, so the parent name is cyclopentane. It also has 2 methyl groups as substituents. Step 1. The ring is our parent chain, cyclopentane. Step 2. Since there are 2 identical methyl groups, we number the ring to give them the lowest possible locant numbers. We assign one methyl group to carbon 1 and then number in the direction that reaches the other methyl group quickest. In this case, that's carbon 2. Step 3. The substituents are 2 methyl groups, or dimethyl. Step 4. We assemble the name 1022-dimethyl cyclopentane. The name perfectly describes how the molecule is built. This covers the fundamental structures and naming conventions for alkanes and cycloalkanes. With these tools, you can confidently identify, draw, and communicate about a huge variety of organic molecules. Okay, that's a lot of ground we've covered today. Let's quickly recap what we've learned and see how we met our initial goals. We started by asking, what is organic chemistry? We learned it's the study of carbon compounds, and that carbon's unique ability to form 4 bonds and catenate, or link together, is what makes this field so rich and diverse. We then moved on to how we represent these molecules. We saw the Lewis structure, the condensed formula, and most importantly for our studies, the elegant simplicity of the skeletal structure. We learned how to translate between these different languages, a skill that is absolutely essential for succeeding in this course. From there, we got into the why. Why do molecules have the shapes they do? The answer is orbital hybridization. We discovered that sp3 hybridization leads to single bonds and tetrahedral geometry. sp2 hybridization leads to double bonds and trigonal planar geometry. And sp hybridization leads to triple bonds and linear geometry. Finally, we applied all of this to our first class of compounds, the alkanes and cycloalkanes. We defined them as saturated hydrocarbons with the general formula CnH2n plus 2 for open chains and CnH2n for rings. We then learned the systematic IUPAC rules for naming even complex branched and cyclic alkanes. You now have a robust foundation in the basics of organic chemistry. You can define what an organic compound is, understand the bonding that gives it shape, and name and draw simple molecules. These are powerful skills that will be your building blocks for everything we'll learn next. Great job today, and I'll see you in the next video.